And today it is time to move forward to a more general situation. So let me recall you the properties of Moyal product first, just to motivate the definitions that I'm going to give. So let, again, V be a vector space. It can be real or complex, it doesn't matter. And let pi be a skew-symmetric endomorphism of V. So you can choose a basis so it's endomorphism of V or matrix of V, matrix of the size equal to the dimension of V. K is the ground field. We assume that pi is skew-symmetric. It means that when you transpose it, you get minus pi. And then it is time to define the Moyal product. Moyal product is an associative product, is an operation, as I say, an operation on the space of smooth functions on V, extended by adding the formal variable h bar, such that first it's bilinear operation, right? Moyal product is bilinear operation, a binary operation on C infinity V. That is to say, this is a star product. It takes an element from A and another element from A and ends up in A. So here are the properties finally. So first of all, star is h bar linear. That is to say, if you take, bilinear actually. It is to say, when you take an element A and multiply it by h bar, and you multiply it by B, you get h bar multiplied by A star B, and the same for the right-hand side, right? In particular, it means the corollary, immediate corollary of this is that it is sufficient, it is enough to define this operation on A and B in the algebra of functions on V. Since using this property and also the additivity of this product, we can extend then this operation from these kind of things to anything. Then the second condition is that the star product is associative. That is to say, for any three elements A, B, and C, we have this kind of thing equal to this kind of thing. That is to say, whatever order of product you take, whatever kind of parentheses you put into this formula, you get the same result. Number three. So it is the following. For any A and B in C infinity of V, so let me first cut down the domain, the separation, just to be able to write a shorter formula. Then the product of A star B begins with usual product of A and B plus something which looks like the form of our series in H bar here we have some operation bk of A and B. And we also assume that bk of A and B are bilinear and bidifferential operators. Bilinear bidifferential operators. For all cases. So what is bilinear, it is clear, and what is bidifferential, it actually means that whenever they fix A, we get just a differential operator in B and vice versa. Or else, probably even easier to define it as by explicit formula. We just give some differential operators, partial derivatives applied to A, some partial derivatives applied to B, multiplied by certain coefficients. And that's actually the most, the easiest way to understand this notion. Number 4 is that the first term in this sum is equal to up to coefficient 1/2 to the Poisson bracket of A and B. Well, Poisson bracket in, let's put it in some kind of quotation marks, because if pi, well, we can actually define Poisson bracket in this way by explicit formula. So probably, okay, let it be Poisson bracket. Because it's not like the usual Poisson bracket, but up to some change of coordinates it is. So let me use pi here and then expand this formula to explain the definition of Poisson bracket. Here, A and B sub pi is equal to the sum over I and j from 1 to n pi ij dA dxi dp dxj. Okay. Actually, this property number 4 can be rewritten in probably more, let's say, insightful way as follows. Equivalent, but equivalent probably more appropriate for future development. You take a commutator of A and B with respect to this star product. Right? And if you look at this first term vanishes because the product of two functions is commutative. Then the second term, which corresponds to B1, will survive, and it gives us the following expression: H bar times the Poisson bracket of A and B sub pi plus something which depends on powers higher than the first power of H bar, right? Moreover, I would say that under some certain small additional conditions, one can show that even if we forget about this condition, we can restore the Poisson bracket from the other conditions. So let me add a few more conditions. So condition number 5 is that 1, the identity function 1, is actually the unit of the product. A is this formal power series space, right? And number 6 is that bk of A, B is symmetric up to the sign. Namely, the sign is dictated by the index k. For instance, it means that B2 of AB is equal to B2 of BA, right? So these two conditions are sometimes omitted. These two conditions can be omitted in some textbooks and some definitions. But actually, if we add this, just this condition, we can restore the properties of the B1 from it. Let me show you how this is done. So suppose we have a product which is associative, which begins with the usual product of functions, and which is h-bar linear, so I don't care about anything. And let me also assume that B2 is symmetric. Then I'm going to show that B1 is actually a Poisson bracket. That is, that it verifies all the conditions we impose on a Poisson bracket. So, proposition. Suppose we have a product of this type. An associative product. H-bar linear product of the form star. Then if B2 is symmetric, then B1 is equal to 1/2 of a Poisson bracket, or some Poisson bracket. So here is the proof. The proof is very simple. We just consider this condition, condition number 1, and expand it in h-bar. So in first degree, of course, in degree 0, we have nothing at all. There's nothing to compare, right? But in degree 1, we have a condition that A times B, B1 of A times B, C plus what else do we have? We have A, B1, B, comma C is equal to sorry, is it correct? Oh, no, it's correct, incorrect. It's on the right. On the left I have this, and also have B1 of A comma C, A comma B, C, like this. Sorry, it's my bad. Sorry. And then also we have on the right A, B1, B, comma, C is equal to plus what do also we have? We also have B1 of A, comma, BC. Okay. I believe I haven't yet made any mistakes. So how can we get H bar here? We can get H bar either from this part, that gives us this term, or we can get H bar from this part, and that gives us this term. Okay, now that's great. Okay, nice. Oh, sorry, if B1 is symmetric, if B2 is symmetric, and B1 skew symmetric, okay, that's also, add this, symmetric. Okay, and B2 be symmetric, B1 skew symmetric, and I probably need the condition that 1 is unit. Okay. Let me see if I need it or not. Okay, I think I can omit it for a while, because let's look here. Let's look here. What does it mean that we have this condition? For instance, fix A. What do we have here then? If A is fixed, that let us see. Okay, just a moment. I need to I just don't want to go further into the details. I just want to get this from the scratch. But it seems that I just want to get the Leibniz rule. So it's almost Leibniz rule here, written here. I mean, it's almost Leibniz rule, except for sorry. Yeah, I'm afraid I cannot just prove this without resorting to some algebraic knowledge which I haven't yet given to you. Okay, so let me skip this for a while and just claim that this is true. And I'll restore it, I think, in a couple of lectures. I'll explain this. So this condition 2 stars, fact, I can use it as a fact. Condition 2 stars is equivalent to say that B1 plus skew symmetricity of B1 I think is B1 is verifies Leibniz rule with respect to both sides. Yeah. I'm awfully sorry. I thought it would be possible to do this automatically, but it seems that I still need some further information to make it work. I'll try to do this. So we'll see if this is possible. So let us then take condition number one and consider the term at h square, h bar square. What do we have then? Again, how can we get h bar square? There are two ways we can do this. First, we can do it by plugging B1 into B1. And second, we can do it by plugging so usual product into B2. So we get like this, formula like this. A B2 of BC, B2 of AB comma C plus B2 of A B C minus B2 of A B C minus B2 of A B C. So I moved all the terms with B2 to the left, and on the right I'll have all the terms with B1. And these terms are B1 of A, B1 of B, comma C, right? And that's more or less it. Minus B1 of B1 of A, comma B, comma C. That's what I think it was, right? Now I symmetrize all these terms. So what do I get? So what does it mean symmetrize? First of all, I move B1 here to the right, so I get B1A, B1 of B, comma C, plus B1 of C, B1 of A, comma B. Right, and then I'll just take the sum of all cyclical permutations. Permutations of A, B, and C. So what do we get in the end? What do we get in the end? So first of all, on the right we'll just have cyclic permutation of B1. So let me denote by B1 of B1AB as 1/2 of B1, of product of a bracket A, comma B, right? And it's easy to see that on the right, after taking the cyclical permutation, we'll have on the right we'll have precisely the expression for the Jacobi identity. That's what we have on the right. Do this. Okay? I mean, I don't know if it is necessary to do this. I think it's a good exercise for everyone to do this permutation. So let me write it down with more details for B2. We'll have B2 of A, B, comma, C. When we permute it, we get B2 of B, C, comma, A, and we get B2 of C, A, comma, B, plus B2 of A, B, C. Here we have B2 of B, C, A, plus B2 of C, A, B. Then we have minus B2 of A, B, C, minus B2 of B, C, A, minus B2 of C, A, B. And finally have minus B2 of A, B, A, B, C, minus B2 of B, C, A, minus B2 of C, A, B. And we have cancellations here. For instance, this term cancels out with this term, just right on the nose, right? Okay, look here. This term cancels out with this term. And this term cancels out with this term, right? No problem. Sorry, someone's calling me. I need to cancel this. Now, funniest thing. So here we had it on the nose for all b's. But now, how about this term? This term cancels with this term, and that is due to the fact that B2 is symmetric. So the symmetricity of B2 is important. Similarly, this term, BCA, cancels out with this term for the same reason. And this term eventually cancels out with this term. So on the left, we'll have 0, and on the right, we'll have Jacobi identity, the expression which stands in the Jacobi identity for this bracket. So it means that if we assume that B1 is skew-symmetric and B2 is symmetric, then we restore the Poisson bracket. Because it verifies the Leibniz rules, it verifies the Jacobi identity, and it is skew-symmetric by our condition, by assumption. Okay, that's good. So this is kind of property we can always demand. So properties 5 and 6 are sometimes omitted, and in future I'll just forget about them. So let me again recall you the properties. Properties of the star product. So first, 0, H bar linear by linearity. Then we have expression, associativity, important, more important first. Associativity. And expression in terms of bidifferential operators. And third important part, it is that B1 of AB is equal to 1/2 of some bracket. And eventually, there are two less important properties, but we will sometimes include them. That unit function is unit, and that the symmetricity of the kth term in this formula is dictated by its number, by its index. So we can put these two later things into parentheses. Now, Moyal product verifies all these conditions. It's not visible if you work with vector spaces, but it is quite evident when you try to go from vector spaces to general manifolds. I mean coordinate changes. So if you change coordinates, then your Poisson bracket ceases to have constant coefficients. For instance, if you had this expression, this equality, pi qj is equal to delta ij, right? Suppose we had this condition. Then it will change to something totally different. That is to say, you have pi I. So instead of pi I, we need to take Si of P, Tj of Q, and what we get in the end will look totally strange. It will look something like sum over A and B from 1 to n, dsi dp a dtj dq a, right? Sorry, not a and b. Yeah, just a from 1 to n minus ds, just the usual formula, dsi dqa dtj dpa, and that is a function. Let me denote it by some expression p ij, ij, depending on s and t, right? So you have some very nasty expressions which you sometimes can turn into this expression by change of coordinates. But how can you tell if your given expressions can be changed into this kind of formula by change of coordinates, and especially if this change can be done globally on the whole space? That's quite a rare thing, in fact. So we need to work with the general notion of such brackets which do not boil down to, the general notion does not boil down in general to this kind of simple formulas with constant coefficients. And what can be done in this case, it is quite a mystery. But because in general, if you just take generic pi ij, which depend on xi, on x, and plug them into the formula for the Moyal product, which I recall looks like this. Di dj are just partial derivatives in directions of xi and xj, right? And apply it to A tensor B. Sorry, A tensor B. Then associativity vanishes, disappears immediately, just because when we proved this associativity last time, I actually used it was some kind of indispensable property of my proof, which could not be changed. I used the fact that this coefficient commutes with the partial derivative. And if it does not, then the whole formula fails miserably. So what to do in general situation is an open question. And it was this question that was called the deformation quantization problem. And it was posed more or less in this way in 1976, I believe, in a series of papers by 6 authors. There was Sternheimer, Flatto, I think I have their names. Oh, yeah, next time. Yeah, so there were 6 authors who wrote 2 large papers and formulated this problem. So our purpose for the remaining part of this course is to solve this problem in most general situation possible. So we are going to begin working in this direction, and the first step towards this ultimate goal is to go from vector spaces to manifolds. So in vector spaces we just had matrix valued functions all around, all on global, given globally in our vector spaces, expressing global coordinates, right? Now we need to work with local coordinates on manifolds and so on, and this brings us to the following definition. And says that a manifold M is equipped with a symplectic structure if we choose a differential two-form omega, so a space of differential two forms in M is denoted by omega, capital omega 2, sub 2. If we choose such that, first of all, d omega is equal to 0. That's easy because every manifold has lots of closed differential forms on it. But the second condition is much more delicate. Omega is non-degenerate globally. So what does it mean that a differential form is non-degenerate? No, it is not. It's just differential two form. It has something to do with orientation. I'll formulate it, but it's a differential two form, and a manifold is actually n-dimensional for some generic, for p-dimensional for some generic p, right? So what does it mean that it is non-degenerate? Omega is non-degenerate if in local coordinates, in some local coordinates, omega, the matrix which represents omega is invertible. Because you see, when we have local coordinates, omega can be written as omega ij dxi wedge dxj. And then here is the matrix. The matrix I denoted by the same symbol omega, and it's just a matrix like this, which is Q-symmetric, of course, right? It depends on x, but it is true for all points in our open neighborhood where we have local coordinates. So they just, and this omega should be invertible. And the inverse matrix of this omega is denoted by pi, and pi will have upper indices, which is tradition in differential geometry. in tensor analysis to switch indices from lower to upper position when you go from the matrix to the inverse matrix. And it's well-based tradition because it's the nature, the behavior of these indices is different. Okay. So, a little lemma which is important for you. Omega is non-degenerate. If and only if omega which if and only if first the dimension of manifold M is even, and second, when you take the top degree of omega, a maximal possible wedge product of omega with itself, then it will be non-zero at all points. So the sketch of the proof is very simple. So first condition is pretty well known. Actually, we all should know that if you have a skew-symmetric matrix in odd dimensional space, then it is degenerate. Because the determinant of omega on one hand should be equal to the determinant of transposed matrix. On the other hand, since we have this skew-symmetricity condition, it is equal to the determinant of minus omega. And by the properties of determinant, the sign appears in the power, okay, let it be dimension of M in front of determinant. So unless the dimension is even, we have a contradiction that some determinant is equal to minus itself. And it only is possible when determinant is zero, right? So that proves number one. Number two is based on the following fact, that when you take omega ij dxi dxj, you can actually take the sum for all ij from 1 to, so let n be the half of the dimension, right, of M. So from now on, I'll denote dimension of M by 2n. So this is actually not just omega, but rather 2 times the omega itself. Because usually when people write down omega, they take the sum for all I less than j. Omega ij dxi and dxj. But it is more convenient for me to use this kind of notation, right? Not to preserve the order, not to look after the order of the indices. Of course, this is just twice this. Then, if I take the wedge product, the power n, what I get here will be 2 to the power n factorial Pfaffian of the matrix omega times dxi, dx1, imagine and so on, dx to n. So here, for instance, I'll get just omega to the power n is equal to n factorial Pfaffian of omega of the matrix times dx1, dxn, dx to n. Oh, very good condition, very good question. Pfaffian is a Okay, there are two ways to write down the Pfaffian. So I can give you explicit expression for Pfaffian, which is actually derived from this formula. So Pfaffian of omega is 1 over 2 to the power n and factorial sum over all permutations in group of permutations of 2n elements minus 1 to the power of s, that is the sign of the permutation, omega s of 1, s of 2, omega s 2n minus 1, s of 2n. So that's actually the formula. You can just expand this expression and get this formula. But it's not quite anti-symmetrization because we have these indices here, right? It's not quite anti-symmetrization. Yeah, but it's something like that. But probably more important is that Pfaffian of omega, when squared, is equal to the determinant of omega. And therefore, Pfaffian vanishes if and only if the matrix is degenerate. I wonder whether you know how to know this fact or not. This is probably, it's a quite popular fact. And the proof is pretty straightforward. You just change the coordinates. So it is easy to see that so you should just take this expression and just put a ij instead of omega, and what you get is something like this. So if you take sum aij dxi dxj and take its wedge product with itself n times, what you get will look like some polynomial of, depending on the matrix A, dx1, wedge, and so on, wedge dx to n. That's evident, right? And this polynomial is universal, some universal polynomial. Then you take the change, the coordinates change. You take dxi equal to some matrix Cij dyj, right? If you make this change of coordinates, then this expression aij dxi dxj, it can be rewritten as sum of b ij dyi dyj, of course, where B is the matrix equal to C transposed times A times C, right? Now we apply this expression to both sides, and we get the Pfaffian P of A times dx1 wedge dx to n. On one hand, it will be equal to P of B dy1 dy to n, right? Just this. Then you substitute this expression here, and you get a very nice formula that it will equal to P of B times determinant of C dx1 wedge and so on dx to n, right? And that's just because of the standard formula for the wedge product. On the other hand, if you take determinant of b, what you get is determinant of a times determinant of c squared, right? And also, you can now take b. So if your matrix is non-degenerate, you can always assume that the matrix is non-degenerate, A, right? Because if it's degenerate, you get 0 already, no problem. So let A be non-degenerate. Then you can take B equal to this kind of thing. Okay? So let's do this here. What do we get? Then it is easy to calculate the P of B, right? It will look like P of B will just so okay, in this case, sum of bij dyi dyj will be equal to 2 times dy1 dy2 plus and so on plus dy to n minus 1 dyn, right, to n. So PB will be equal to 2 to the power n times n factorial. It's just straightforward computation, very, very easy, right? So what we get if we use this expression here, we get P of A dx1 dxn to n will be equal to 2n to the power n factorial times determinant of C times dx1 dx to n. On the other hand, here the determinant is equal to 1. Right? So determinant of A is equal to 1 over determinant of C squared. No, that's more or less what we have here. Right? Is it true? Oh, sorry. Up to somehow I have changed. Yeah, the only problem is that I have the incorrect order. I don't quite understand. I don't see how I got with determinant of C, not C minus first. It might be some problem with this. Maybe C minus first should be. Okay. Sorry for this. So check it. Actually, I have it written in my textbook, but I prefer to do this to do this from the scratch, and I ended up with some very strange. It should be minus first here. I don't know why. Actually. Oh, sorry. Of course it's minus first. And the problem is because here we go, they have the formula for x I instead in terms of yj, and here I need the formula of yj in terms of xy. So it's minus first, of course. Now it's correct. And and that is precisely proves the formula. Pfaffian exists. Yeah, okay. I'm eventually done. Okay then. So you can see that the existence of symplectic structure is quite a big condition, I'd say. It imposes certain conditions on the topology. I hope you will do some problems. Hope we'll discuss some problems today and see what properties of symplectic structures, what properties on the topology of our manifold the existence of symplectic structures impose. Okay, so how much time do you still have? 25 minutes. 25. Yes. Oh, that's great. That's plenty of time. So let me go on. So I suppose I have a symplectic structure on a manifold M of dimension 2n. So I'll denote it like this. So first of all, then I will speak that I have symplectic manifolds. Symplectic manifolds. So let me give you a few examples of symplectic manifolds. Though the example number 0 is R to n with the form given by dp1 dq1 plus and so on plus dpn dqn. That's the standard symplectic form on a Euclidean space. But then here comes a bit less simple but still very standard symplectic form, which can be associated with any manifold whatsoever. So let X be a smooth manifold. If you remember, T star of X denotes the space of covectors on X. That's what they call the cotangent vector bundle of X. In local coordinates on X, local coordinates on X, let x1 through xn be these coordinates. We have coordinates on T star of X associated with this set of coordinates. So what are these coordinates? So every point in T star of X is a covector on X. So any covector xi in T star sub X of xi of X capital can be written as the sum xi1 dx1 plus and so on plus xi n dxn, then the coordinates of psi in T star x are precisely psi1, psi(n), x1, xn, where x1, xn are the coordinates of the point x. Right? So these are the coordinates. So in some sense, we can say that psi I is just pi, nothing else. Okay? And let's consider the following differential form.
So pi is just function.
P1, pi, well, it's not functional. It's actually coordinate on the space of functional. It's kind of the coefficient that stands in front of the functional dxi. You see, dxi is a functional, yeah, is a covector. But then you can actually change it a little bit. So consider the differential one form on T star of x given by the coordinates, given in these coordinates by the formula. P1 dx1 and so on, Pn dxn. You see, this expression seemingly depends on the choice of coordinates, but in fact it does not. Check it. Yeah, because of the tensor rule, when you change coordinates of x, when you change x to xi to xi prime, you simultaneously need to change pi to pi prime. And the tensor rule will cancel out. Right? Check that this is well defined. This is denoted by as L. This is called alpha. So alpha is canonical differential one form. You can actually define it in a coordinate-free way. We can talk about this at the seminar today. So let us skip it for a while. But then I just put omega equal to d alpha. And of course, d omega is equal to d square alpha is equal to 0 by the properties of the de Rham differential. And moreover, omega in local coordinates will be equal just to dp1, which dx1, plus and so on, plus dpn, which dxn. So it is non-degenerate. Yeah, it is exact, but nobody has forbidden us from it being exact. It can be exact, it should be closed, but every exact is closed. So that's not a problem. Okay, and example number 3 is the following. When you have a complex manifold, so suppose you have X complex manifold, then you can sometimes equip it with a special kind of Hermitian structure. Such that its imaginary part will verify the condition. So this imaginary part is always a differential two form. I think it is a good exercise for you to prove that whenever you have a complex manifold and you have a Hermitian structure in this complex manifold, then taking its imaginary part of this Hermitian structure will always bring you to the differential to form. Always give differential to form. So when you take this differential to form, and sometimes it happens to verify the condition that its the Ram differential vanishes. In this case, X is called Kähler manifold. There are plenty of examples of Kähler manifolds. Well, for instance, every complex manifold of complex dimension 1, complex curve, is Kähler just because there are no differential forms of degree 3 and higher. Sorry?
Degree 3 or 2?
Degree 3. If you take a complex manifold of complex dimension 1, and its real dimension is 2, and there are no complex and there are no differential forms of degrees higher than 2. So every complex curve is symplectic. Sorry, is Kähler. Is Kähler. Well, with any, more or less with any Hermitian structure on it. But then there also exist other examples like complex projective spaces are Kähler. Then you need to introduce the differential, the form, Hermitian form, which is called the Fubini-Studi form. What is good about this? It is that when you have a Hermitian structure, it is non-degenerate automatically because it is sesquilinear positive definite, right? And it means in particular that its imaginary part is non-degenerate. So these are automatically symplectic. Here is one more large source of examples. So what can we do with symplectic manifolds? I think I'll prove one result finally, and then we'll make a break today.
These examples, how are you thinking about
Huh?
degeneracy?
Sorry? In the third example. So this, here the non-degeneracy is evident, right? It's just from the local coordinates. It follows from just from the local expression.
You write the matrix
and here the non-degeneracy follows from the fact that our differential form is just the imaginary part of a non-degenerate Hermitian matrix. You see, that's kind of, I mean, of course you need to prove this, yeah. Suppose you have a Hermitian matrix. You know, suppose it is non-degenerate Hermitian, positive definite Hermitian. How do you prove that its imaginary part is non-degenerate? Well, it's a good question. It's in linear algebra. I think we'll discuss it today, okay? It's an question in a linear algebra, okay? But here is one more thing about the symplectic geometry. So suppose M, comma omega be a symplectic manifold. So let be a symplectic manifold. Then for any couple of functions, for any pair of functions f and g, smooth functions on M, I can define their Poisson bracket. Given, well, sometimes people introduce sign here, but I prefer to work without signs. So I'll have something like this. We have the inverse matrix pi of omega. I put pi ij here, and then I take df dxi dg dxj, sum over all ij from 1 to 2n. That's the coordinate expression, but in coordinate-free expression, you can rephrase it like this. So if you have a differential form, then its inverse is a section, is what they call bivector field. So a differential form is a section of the bundle, so of a tensor square of a cotangent bundle of x, of m, sorry. Right? Then one can show that its inverse is a section of the exterior square of tangent bundle of m. Such sections are called bivector fields. We'll talk about bivector fields and polyvector fields in the near future. Now it is sufficient to have this kind of intuition here. And just like differential forms can be paired with vector fields and give you functions, just like this, you can take polyvector fields, or bivector fields in particular, and pair them with differential one forms, with covector fields. So differential one forms are covector fields.
When you say bivector field, you mean that we take a vector field and its exterior product is...
Yeah. So, but you cannot take a bivector a vector field and take its exterior product with itself. You get zero. But yeah, with some other vector field. Yeah. So roughly speaking, every element here is a linear combination of xi, which yi, where x and y are vector fields. You can write every element here in this form. Right? But what is good, now you can pair this bivector field with covector fields, df and dg. So as you see, for every symplectic manifold, we have a well-defined bilinear operation on functions. And of course, this operation verifies 2 out of 3 conditions which we usually impose on Poisson brackets. That is to say, it is skew-symmetric, which is evident just because because this product is skew-symmetric, right? But it also verifies the Leibniz rule, and that follows from the fact that this pairing is linear over functions, and differential of the product is equal to, by Leibniz rule, to the product of g dh, the sum of g dh plus dg times h. So how about the third condition, the important condition, the Jacobi identity? Claim the Poisson bracket verifies the Jacobi identity. I prove this, and that will be all for today. Proof. Let us consider the vector field. X sub f equal to pi. So let me write this down in coordinates. Pi ij df dxj. So the summation over j is understood, right? What in somewhat informal terms, this vector field is obtained by raising the indices of the differential of f with the help of the bivector pi, right? That's raising the indices. Then, of course, just by definition, Poisson bracket of f and g is equal to minus xf of g. If you just plug this into the formula, you'll see that this matches perfectly, right? Just the sign is different, but the sign can be corrected by changing the order, and that's precisely why we have it here, right? Okay. Now, if we take the differential form omega, then by definition, it's the Ram differential with is equal to 0, right? Hence, we have the following formula. For any vector field, well, you probably know the Cartan's magic formula for the Dirac differential. I hope you do. You remember this Cartan's magic formula that if you take the Ram differential and commute it or anti-commute it with the how do you call this? I quite forgotten. It's not convolution. It's contraction of a differential form alpha omega, right? X, then what you get will be the Lie derivative with respect to x. So let me do this. So that's true for all vector fields, right? And now I do this for the vector field equal to x sub f. So what do I have? L x sub f of omega is equal to what? It is equal to d I sub xf of omega plus ix d omega. So now this term disappears, right? And we have this here. That's true for any vector field and for any differential form. Now what I do, I take this and what do I do further? Sorry, I thought I remember this pretty well, but it seems that I am I actually want to show that this is equal to 0, right? That's what I want to show.
Contraction of xf with omega is just df up to some.
Yeah, precisely. That's what I really want to do. Oh, yeah, sure. Okay. Let us take any vector field f, y. And let's take yxf, ixf of omega and compute it at y. What do we have? Then up to this coefficient, we will have precisely omega xf comma y. Now, if you again use the explicit formula, then what you get will be 2 omega ij pi I k df dx k. Then we have y j, right? Now, this is actually equal to delta up to the sign, to delta, that's minus delta jk, right? Because pi is inverse to omega. So we have df dxk yj. And that's precisely, by definition, y applied to f. Or, which is the same, df applied to y. Up to the coefficient and probably the sign. So what we have here is differential form df. So d applied to df is equal to 0. As I promised. Let us return back to this formula. What do we have? We want to prove that this triple Poisson bracket verifies the Leibniz rule, verifies the Jacobi identity, right? So let me write it down as up to the sign minus xf of Poisson bracket of G and H. On the other hand, what we have here is pi of df, dg, dh. Now, by the properties of the Lie derivatives, we can apply Lie derivative with respect to xf to every term on the right. So it will be equal to minus Lie derivative of x sub f applied to pi, applied to df dg, minus pi Lie derivative of x applied to df dg, sorry, dg dh, dg dh, minus pi of dg Lie derivative of xf dh. So since Lie derivative of omega with respect of xf vanishes, the same is true for its inverse. So the first term vanishes. As far as the second term is concerned, as you remember, Lie derivative commutes with the Durand differential. So what we have is minus pi d Lie derivative of xf applied to g, that is xf applied to G, comma, H minus pi dg dxf applied to H. Again, by definition, by that property on the left, what I have is pi, d f g, comma H, plus pi g dg d f h. And by definition, that's precisely this expression. And that's the Jacobi identity. Because as I explained, Jacobi identity can be written as the condition that the bracket verifies the Leibniz rule with respect to itself. So that's precisely the Jacobi identity. I think that's it's a good time to make a break. So next time I'll talk